So hello everyone. Today we are going to solve some quadrilateral problems. It's the chapter 4 of the AoPS Volume 2. So let's starting with question number 60. So in this diagram we have the ADM. We have the ADM that's parameterized as alpha equal the ACD is alpha, and we have the ABM is beta equals to the ACB is beta. So we want to prove the AB equals AD. So there are some ways to do it, right? So the first is the sixth side. So we want to prove the side equals side, right? The second way maybe try to see the angle, right? If we can prove alpha equals beta, maybe we can prove it, right? So if we see, let's try some angle first, okay? So this angle is the common angle of the AMD and the ADC, right? So that's why the ADC is equals AMC, right? So if this angle is gamma, then this angle is ADC is also gamma, right? This is gamma minus alpha. Then this angle will be the 180 minus gamma. If this angle is 180 minus gamma, this angle is 180 minus gamma minus beta, right? So by take a look at all these angles right now. This one getting into a triangle, and the alpha minus gamma plus alpha 180 minus gamma minus beta. When you add them together, it's becomes the 180 equals 180, right? So the angle chasing seems not to work. Okay, so not working. Okay, if angle chasing not working, now we already see the triangle, the ABC, and the triangle, the ABC and the AMB, right? So we know the angle ABC. Okay, we have a beta is angle ACB, right? Equals beta of this is the angle ABM. Then we know the common angle, right? Angle BAC equals to angle MAB, right? So now we can set up the similarity, right? So this AA rules, they are similar, right? If they are similar, that means the AB, the corresponding the side will be the AC is equal to the AM. The corresponding side is AB. So we have the AB square is equal to AM times AC. Okay, so this gives us hint. Okay, we have another similarity here, right? Can we prove it? It's the can we also see the AD square equal this, right? So we have the triangle ADM and the triangle ACD. Okay, let's see. So we have the alpha equals the angle ADM. This is the alpha equals ACD. Then we have the angle CADAM. This is the angle CAD. This is the same angle, right? So this is the AA rule, right? So now we have the AD, the corresponding to this angle, so it's AC. Then we have the AM corresponding to alpha equals AD. Then we can have is AD squared is AM times AC, right? So now we use the similarity, we can prove that AB equals AD. Okay, so do angle chasing first, because angle is always easy to solve, right? And because, I mean, the angle chasing doesn't work, so now we use the similar triangles and just to seek from the side, okay? So that's how we deal, normally how we deal this type of problem. So question number 61. So we have a quadrilateral ABCD. So we have a quadrilateral ABCD. Let's see. Inscribed in a circle. Uh, 8, 15. It's 8, 15, 12. Given AC is the diameter, that means this, right? Okay, that means it's 90 degrees. So we know it's 17 pi is equals to the 2 pi times r. Then we know that d equals 2r equals 17, right? So AC equals 17, and the center here is the O. What is the length of the other diagonal, right? So the goal is to solve the BD. Okay, so if we know this is 17, we can solve AD, right? And if we know we can solve the AD, right? Once we solve the AD, we can use the Ptolemy Theorem, right? Ptolemy Theorem tells us for a cyclic quadrilateral ABCD, then we have the AB times CD plus AD times BC equals the two diagonal is AD times BD. Okay, to prove this, use the similarities. Okay, or there are many ways. I think what I see is the similarity is the most popular ways. Okay, there is another way is to the circle inversion. Okay, now let's use this one directly. Okay, I will maybe post another video for the proof of the Ptolemy theorem. So now you can see you have 17, you have 12, right? So AD equals to the 17 square minus 12 square is equal to the 5 times 29, right? Is equal to root 145, right? So now you can see if you solve the BD, right? So BD times 17 is equals to 15 times the root 145, then plus the 12 times the 8. Okay, then you can solve the BD equals the 17, 15 root 145 plus the 96. Okay, if you know the Ptolemy theorem, this one is very simple. Next problem is the problem 62. So we have a quadrilateral inscribed in a circle, right? Have the 25, 39, 25, 39, 60, and the 52. Okay, let's do A, B, C, D. So we have the 25, 39, 60, and the 52. Okay, so the question asks us, what is the diameter of this? What's the diameter of this? Of this circle, right? So in order to do the diameter, what we know is 2r equals a over sine a, right? Equal b over sine b equals c over sine c, right? This will help us to relate with the circumcircle, the radius of the circumcircle with a triangle inscribed in this circle. So this is the law of sine, right? So I think if give us we need a triangle. So in order to have a triangle, we need a side and an angle, right? So let's see if this angle is alpha, then this angle is 180 minus alpha, right? So we can use the law of cosine to do the AC, right? So the AC square equals to, from the triangle ABC, right? You can have it's the 25 square plus the 39 square minus 2 times the 25 times the 39 is cosine alpha, right? And also from the triangle ADC, right? You can have the AC square equals to the 52 square plus 60 square minus 2 times the 52 times the 60 plus, right? 180 minus alpha is plus. So by doing this, okay, we can see we can directly solve the cosine alpha, right? So the cosine alpha, so we know it is the 25 square, right? Plus 39 square minus 52 square minus 60 square, right? Okay, let's assuming this is alpha. Okay, let's do positive. It doesn't matter. So plus and minus. Okay, so now we have this part is equal to the 50 times 39 plus the 52 times 120 of the cosine alpha. Then we can solve the cosine alpha equal to 33 over 65. Okay, if cosine alpha we know, then we can solve the sine alpha, right? So the sine alpha is equal to the 65, right? 65 square minus 33 square is 232, right? And 98 is equal to 65, then 7 times 8 is 56 over 65. Okay, so we know the cosine alpha and we know the sine alpha, right? We already have something we know, and the only thing we're missing is AC. So we can apply the AB back to any one of them, right? Now we can solve the AC. So AC is equal to 52 square plus 60 square minus 2 times the 52 times 60 times the 33 over 65. Take the square root. Then this one tells us it's 56. Then the 2r is equal to the AC over sine alpha is equal to the 65. Okay. So yeah, I mean, there is involved with a lot of calculation, that's for sure, but it's still manageable when you starting to familiar with the law of sine and law of cosine. Okay. Problem 63. So we have a suppose an angle BAC. So we have an angle BAC is rotated about the center of the O, right? So this is the center O. So the center O moves the A to the A prime, right? So if this angle is alpha, right, then the corresponding sides also rotating alpha, right? So the corresponding sides are this side, right, is versus to this side. So this angle is also alpha, and this side get rotating to this side, right? So this angle is also alpha. So we want to prove the A prime, A prime, M, Q, N is on a circle, right? So in order to prove the 5 points on the circle, we know how we prove the 4 points on the circle, right? In order to prove the 4 points on the circle, either this one plus this one is 180, or the other thing is to prove this angle equal this angle, or you prove any of this angle, right? Just for example, we use this chord, then this angle equal this angle. You can all these ways can help you, right? Now let's see which one. Okay, let's see the angle. Let's see the point A, B, O, A prime. Okay, so did you see the A prime is a chord? Then span the angle alpha here, span another angle alpha here. So this for a concyclic, right? And if you watch the other one is the AO C, the A prime, right? Then we have alpha here, so they also concyclic, right? Because these two are share a common, see A prime, A prime, right? A triangle can fix, this triangle can fix a circle, right? So B is on this fixed circle and C is on this fixed circle, right? So that's why the A prime, B, C concyclic. Okay, so problem 64. Okay, so a parallelogram. Okay, so I think this is Bulgaria 1993 of the Math Olympiad. Okay, so we have the A, B, C, D, right? We have the BAD is given, and the bisector of the BAD, the angle bisector of the BAD, intersect of CD at L, and the line BC, so this line extension, at K. Then let O be the circumcenter of the LCK, so the perpendicular bisector, right? perpendicular bisector. So this is the O. Then the circle will be like okay, so the circle is like this. Then we want to prove the quadrilateral. Let me use another color. Is BD OC. We want to prove the BDOC, okay, is concyclic. So goal is concyclic BDOC. Okay, so in order to prove the concyclic, we can prove either we already talked about it, right? So let's parameterize some angle first. Angle alpha, right? AD parallel to BK, right? So this angle is also alpha, right? And this CD parallel to this angle is also alpha. So we see there is an isosceles triangle and another isosceles triangle. So in order to see its isosceles triangle, we can parameterize the sides, right? So this is also alpha. So this is the M, this is the M. Then this is the N minus M. Let's use P. Okay, P minus M. This is the P. This is the M, and this is the P minus M. So these are all the sides. Let's connect the OB. Okay. Okay, so we have this one is P minus M, right? And this one is P minus M. Okay, so we have a kite. So because these are on the circle, right? So this is the radius, for example. This is the A. This is the A. Then this is the P minus M and P minus M. There is a kite here. So this angle is 90 degrees, right? In the kite is 90. This kite is 90 degrees. Then we can see the angle. What we want to prove is we either want to prove this angle equals this angle. This angle is alpha, right? We can prove this angle equals this angle. So now let's see, okay? So because it's a kite, we can parameterize this angle and this angle, right? So if this angle is beta, then this angle is beta, then this angle is beta. So this is the beta minus alpha, right? And this angle is also beta minus alpha. Okay. So now we can see the triangle OCD and the triangle OKB. Okay. In triangle OCD, why I see triangle OCD? Because triangle OCD have this angle. Triangle OKB also have this angle, right? So, and we also have the equal sides, right? Because in the OCD, you can see the OC equals A, then OK equals A, right? It's S, right? And we have a beta and a beta, right? So angle OCD is beta, then angle OKB is beta, right? Then the the side we know the CD equals P, right? And the BK equals P, right? So these two triangles are what? They are SAS, they are congruent. OCD congruent to triangle OKB. If they are congruent, that means angle, this angle equal this angle. That's angle ODC equal angle OBC, OBK, right? I mean, if these two angles are same, right? These two angles are spanned by the same arc, same chord, either the arc, right? So CO spanned angle ODC equal to angle OBK. Then what we know is the BDOC are concyclic. Okay, so yeah, so we can see in order to prove the concyclic, and we need to do either angle tracing or use, when you're angle tracing, we also tells use the similar triangles, right? Because when you do angle tracing, you can trace some angles, but those angles cannot help you to locate it in the angle you wish to prove the concyclic. But those angles may help you to see the similar or congruent triangles, and using the congruent triangle or similar triangle as a bridge, you can map to the equality of the other angles, which helps you to achieve the angle you wish to know to prove the concyclic. Question number 65. So we have the side ABC, ABCD. ABCD, okay, is a square, and is also the hypotenuse of a triangle APB, and APB is outside. So we have a P APB, right? Then prove that angle bisector of the APB bisects the area of ABCD. So we have an angle bisector. Okay, 45 degrees, right? So we want to prove this one. For example, it intersecting at 2 points at the E and F. We want to prove the EF bisected the area of the ABCD, right? So let's see what kind of things can bisect the area of ABCD, okay? A cutting line through the center O can always bisecting this area. Okay, if you're bisecting the center, right, you can do the height, right? Because it's the center, so you know this angle equal this angle, right? 90 degree equal 90 degree. The half of this equal half of this. The two triangles are similar, right? So similar, you can see this, the section of this part, right, is equal to the half of the square. Take out this triangle, adding this triangle, right? So that's why this side is half of the square. So now the problem converting to, we want to prove the angle bisector of the BEF, PEF, right, is passing the center of the square, right, passing the O. Okay, so how about let's proving in that other way. Okay, let's connecting the PO, and we prove the PO is the angle bisector. Okay. Okay, so Now let's connecting the AO and the BO. AOBO, this one is 90 degree, right? We have a 90 degree, right? So this one tells us the concyclic is APBO, and the AB is diameter, right? So we have a circle, right, with tangent at the B and A. That's making this happen, right? Okay, then you can see if this is the case, right? We know the AO equals BO, right? So the AO arc equals to the BO arc, right? So the AO arc span this angle, the BO arc span this angle, right? So that's why this is the 180. This is the 180 degrees, right? So this is 90 degree. This is 90 degree. Then the inscribed angle is 45 and 45. So that's why the PO is angle bisector. Now we can conversely we can see the O angle as an angle bisector, PEF as an angle bisector, passing O. Once you know it's passing O, we know it's cutting the square into two equal area part. Okay, so yeah, I mean the rest of the problem, especially the last problem, is pretty long. Okay, so let me take another video for the rest of the three problems. Okay, thank you. Bye bye.